Hello, everybody. My name is Octavio Pacheco. My mentors are Dr. Nathan Thompson, Dr. Elizabeth Berman, and Dr. James Stick. The name of my project is Scalable Grover's algorithm using dynamic, using dynamic learning improves quantum speedup. So that is a mouthful. What does that mean? Basically, I worked with a quantum algorithm, particularly Grover's algorithm. This algorithm it is an unstructured search algorithm. What that means is basically if you have a list with so many items in it, and there is an item that you are trying to find, this algorithm helps you find that item. So, for instance, I have provided here in the bottom left corner an example where you have a list with 4 items. If you were to ask a classical computer to find this item for you, what would it do? Well, it will look at the first item and realize that that is not it. Then it will move on to the next item, which is also not the one that you're looking for, and so on until it finds the item that you were looking for. In literature, we call it the winner item. So here I want to point out that a classical computer will take at least 3 attempts before finding the item that you were looking for. Granted, here I provided the worst case scenario where the last item in the list is the one that you were looking for. But what Grover's algorithm does, it provides a quadratic speedup. So for instance, in this case, with the 4 items in the list, Grover's algorithm will only take 1 attempt to find the item that you were looking for. So what does this mean? For instance, if you have larger list, let's say if you had 1 million items on the list, it would be very not beneficial to look at every single one of them. So you only will have to look at 1,000 of them, the square root of that, which is a significant difference from 1 million to 1,000. And I have provided a plot on the bottom right corner where you can see the deviation from the random guessing, the classical guessing, compared to Grover's algorithm. The larger your system gets, the more significant the difference is between the quantum version and the classical version of the algorithm. So how does Grover algorithm works? Well, basically, Grover's algorithm has 3 main parts. The first main part is you have to put everything in a superposition state. So for the purposes of this project, instead of using items, as I've been calling them so far, we use quantum states. And so far, we've been working with the 2-qubit state. So here for the 2-qubit state, you have 4 items on your list. You have to put all of them in a superposition state. That means that basically, if you were to just randomly guess one of them, they all have the same probability of being found. And that is the first purple line that we have here. So the goal is that superposition state, we want to make sure that we pick the right item. So we want to eventually, that purple line, make it go up and align with the vertical axis, which we call the winner state. So that's the final goal. So once you put all of your states in a superposition state, now you do a phase inversion, which is basically applying an oracle. What this does is just basically it gives a negative sign to your winner item, the item that you are looking for. What this causes overall, it reduces the overall average of all the items of being found. And as you can tell now, because the winner state has a negative sign attached to it, now we are on the negative vertical axis. So then at this point, then comes the diffuser portion, which is the focus of this project. This diffuser, what it does is an inversion about the average. What this means is that, okay, you were in a negative phase really low. So once you use your diffuser, it flips it back up, but at the same time, it amplifies the amplitude of your winner state. You may notice that the purple line on the plot on the right is closer to the vertical axis, to the vertical axis than the first purple line was. So that is how Grover works. And I have provided here at the bottom just a version of what Grover's algorithm looks like. Here I use IBM Quantum Composer, where I have divided the 3 main parts with the dotted lines. So previous work done for this project. So basically, I am working with something that other students in the research group that I am working for did in the past. So basically what they did first, they also started with the 2-qubit case, and they defined a Hamiltonian. A Hamiltonian is a time evolution operator. I will touch on that a little bit more in the next couple of slides. Then once they have the Hamiltonian, they divided it into different time chunks. So basically, what happens at what points. And then once they have their time chunks, they define a quantum circuit for their Grover's version. And from here, they just went to some other research that is out of the scope of this project. Well, what we've been working for this project is a backwards version of this. So we start defining a quantum circuit, and then we find our time chunks, and then we find a Hamiltonian. Okay, so how do we come up with these quantum circuits? We are lucky that quantum states are actually quite easy to visually and geometrically represent. We use what we call the Bloch sphere. The Bloch sphere is on the right, is just a regular sphere, and you can represent any quantum state on it. It's basically you have an arrow pointing at one part of the sphere, and that is a quantum state. If the arrow is pointing some other way, that's a different quantum state. Well, after doing the calculations, you hopefully point the arrow where you are trying to make it point. To do these changes in the Bloch sphere, I use all of these equations and matrices that are here on the screen and a couple gate identities. They are called rotation gates. They are rotations about the X, Y, and Z axis. So again, basically, if you are pointing up, what these rotations do, they move you to another point on the sphere. So that is what these do. And also the couple gate identities that I included here is just so we can write hopefully better and improved version of our algorithm. So I started working with the model on the left. That was a version for the diffuser portion of Grover's algorithm. And from that model, I then used all of the formulas that I showed you in the previous slide. And I came up with the circuit on the right. You may be instantly able to notice that it looks shorter. It has less gates, which is something that we were looking for to make it simpler. And from there, we have selected at this point 3 different time chunks. This is something that we will be able to change according to future calculations, but there is just some room to explore in the future. So now that I have my quantum circuit, we use the time evolution operator equation that it is on the top left. Again, that equation, what it does, you start with an initial state and you end up in another state. So that form of that equation, we have an exponential form. So what we are looking for is the H item in it, the Hamiltonian. To get that, I use once again the rotation gates on the right, but now I use their exponential form. Why is that? It is because because they are already in an exponential form. So it is quite a simple translation to have the rotation gates translated into the time evolution operator. So once you put everything together in your circuit, what I did, I came up with this equation in the bottom left, where I have the constants that I use to rotate the angles accordingly and my gates. And once I got that, then you plug it into your time evolution operator, the Hamiltonian. So what comes next after finding the Hamiltonian? Then we actually tested in the code just to make sure that we get the answer that we were looking for. So to do that, we use MATLAB. MATLAB has come again in some presentations earlier. It is a very useful programming language to represent, in our case, quantum states, because MATLAB comes from matrix laboratory. So I showed in the previous slide some matrices that are exactly the ones that take you from one state to another. So basically, what we're doing at this point, we are testing those calculations into the code and verifying that we do get the quantum state that we were looking for the 2-qubit case. So now the next step after we test our functions that we have that we are implementing, we are going to use Bootstrap. What Bootstrap is basically we're going to start with the 2-qubit case, and we are going to translate the information that we learn and train from the 2-qubit case for the 3-qubit case. And then the information that we get from the 3-qubit case to the 4-qubit case and so on. We are probably just going to go up to, at the most, 8-qubit case 8-qubit case because it becomes quite large, the system, even with just 3 qubits, then you have 8 states, and basically you get 2 to the n state. So it becomes quite large, and it becomes rather impossible to test it in classical computers. Yes, we have these tools available, quantum composers that do an amazing job at simulating the systems, but they do have a limit. And clearly here, at least in Wichita State, we don't have access to a quantum computer. So at that point of the project, again, what we are going to be doing for the larger system, we're just going to be playing back and forth with our phase inversion and the diffuser. We are going to assign that negative sign to the item that we are trying to look for as many times as we need, because the larger the system, the more times that you need to apply this portion of the algorithm, and then using our version of the diffuser to hopefully make that purple line fully aligned with the winner state. And that's the end of my presentation. Thank you very much.
So, on a practical level, like what industries do you think would be most impacted by your research? And practically, how would you implement them? Would this be used for like training AI, or what did you have in mind for the findings that you have?
So the final goal is, yes, to use it in some type of artificial intelligence and neural networks. But some like first applications for this algorithm would be for companies like Google or Amazon, that we know they have really extensive lists of items that they are trying to find, and this algorithm will provide that speed up that they can find whatever they are looking for much faster. But yes, the final goal is we want to apply this at a neural network. Good question.
Last question.
What did you like best about doing this project? You seem to have a high level of energy and excitement about it, and there was a lot of mathematics. So what did you like best about doing this presentation?
So I was always very intrigued by quantum mechanics, and as a physics student, when I started my degree, I thought about taking those classes, and I was like, oh, that's going to be so hard. That is going to be so difficult. Once I made it there, I just found a passion for quantum mechanics in general, and and then the combination of quantum mechanics and machine learning that just provides these tools for these big companies such as Google, Microsoft. There is a lot of time and money invested into this type of research nowadays. That is also a plus. But just learning something that most people think would be extremely hard, that it turns out it is not as hard as you think, and that is what I like the most. That feeling of starting to understand some of those papers that I always thought I will never be able to understand.
Thank you, Octavio.